Welcome to today's lecture. In the last lecture, we have seen Unit 2 angle modulation. We have seen the definition for angle modulation and we have seen the types of angle modulation. In today's class, we are going to see generation of angle modulation. In particular, we are going to see generation of narrow band frequency modulated wave. This is our lecture 2 in Unit 2. Title of our unit is Angle Modulation. So far we have seen what is the definition for angle modulation. We will see what are all what are all we have seen in the last lecture. Then we will move on to today's topic. We have seen the definition. What is the definition for angle modulation? Varying the frequency or phase of the carrier in accordance with the message or modulating signal. When we vary frequency of the carrier signal, then we refer that type of modulation as frequency modulation. When we vary phase of the carrier signal in accordance with the modulating signal or message signal, then we refer that modulation as phase modulation. So these are all the two types of modulation coming under angle modulation. One is with reference to phase and one is with reference to frequency. After the definition, we have seen the time domain expression for frequency modulation as well as phase modulation. What is the time domain expression for phase modulation? We will refer in terms of S of t is equal to AC. AC is always constant, that is amplitude of the carrier frequency is always constant. Therefore, cos of 2 pi fct plus kp m of t. Kp is the proportionality constant, therefore phase is varied in accordance with the modulating signal. Second one is FM, frequency modulated wave, time domain expression AC cos 2 pi fct plus 2 pi kf integral over 0 to t m of t into dt. So this is the time domain expression for frequency modulation and the time domain expression for phase modulation. Apart from this, we have seen what is the important parameters. What are all the important parameters in angle modulation? First one is frequency deviation. Frequency deviation, that is how much or how maximum the departure of the modulating frequency from the message signal. That is del f is equal to kf into am. It is independent of frequency term, it is dependent only on the amplitude of the message signal, that is maximum departure of your carrier frequency from the center frequency. Second important parameter is modulation index. We refer modulation index here using beta. In amplitude modulation chapter, we have referred modulation index using mu. The modulation index is referred as beta. Beta is equal to del f. Del f is the frequency deviation, del f by fm. If we have del f less than 1, then we characterize that type of modulation as narrow band frequency modulation. If we have a beta, that is modulation index greater than 1, then we characterize that kind of modulation as wide band frequency modulation. And the third important parameter we have seen is deviation ratio. Beta we refer for a sinusoidal modulation. Deviation ratio, when we have non-sinusoidal modulation, we refer beta using D. D stands for del f by fm max. So these are all the three important parameters which we study in angle modulation. And we have also seen the frequency spectrum for narrowband modulated wave. In the last lecture, we have seen there is center frequency around plus fc and minus fc, two sidebands at minus fc plus fm and minus fc minus fm 0. So this is our 0 and again LSB and USB. fc plus fm, fc minus fm. So this is our upper sideband. AC beta by 4. This is our lower sideband having same magnitude. Carrier frequency is having the magnitude of AC by 2. Here also AC by 2. This is our LSB. having a magnitude of AC beta by 4, AC beta by 4. So by looking into the frequency spectrum, there is no difference. That is the spectral content for amplitude modulation and spectral content for narrowband frequency modulation are same. Spectral content are same. Maximum transmission bandwidth for narrowband frequency modulation is higher frequency minus lower frequency. Therefore, the bandwidth is 2 FM for narrowband frequency modulation. In today's class, we are going to see generation of narrowband angle modulation. In today's lecture, we are going to see generation of how to generate the narrowband angle modulated wave. First, we will see for phase modulation, then we will move on our topic to frequency modulation. Phase modulation. What is the time domain expression for phase modulation? As Pm of t is equal to AC, just now we have seen, right? Cos 2 pi fct plus kp m of t. We know the cos formula, cos of a plus b is equal to cos of a plus b, which can be expanded as cos a cos b minus sin a sin b. We are going to take 2 pi fct as a, kp m of t as b. Therefore, rewriting this equation, S Pm of t is equal to AC cos 2 pi fct plus cos kp m of t minus sin, AC is the common term, therefore minus sin 2 pi fct sin of kp m of t. Since we have taken narrow band, for a narrow band, we know this modulation index beta will be less than 1. That is, kp m of t will be less than 1. Less than 1. Therefore, we can replace cos kp m of t as 1, and then sin, minimum value for cos is 1, and sin kp m of t is theta value. Therefore, kp m of t. This is our value, right? Minimum. Therefore, kp m of t. Therefore, by substituting this, S Pm of t is equal to AC cos 2 pi fct. This whole term will become 1. Therefore, AC sin 2 pi fct. This whole term will become kp m of t. By rearranging the terms, AC cos 2 pi fct minus AC, by bringing the constant terms in front, AC kp m of t into sin 2 pi fct. So, this is our final expression for narrowband modulated phase modulation. Now, we will see what is the block diagram for this implementation. So, we are applying the message signal m of t. We are having a carrier signal, here carrier, using a crystal oscillator. Therefore, carrier signal is, we know that the AC cos 2 pi fct, when we give a phase shift, minus 90 degree phase shifter, applied to the second input for the product modulator. So, one of the input for product modulator is message signal and another input is phase shifted carrier signal. Therefore, AC cos 2 pi fct is our carrier signal. Phase shifted version will be AC sin 2 pi fct. Output from the product modulator is fed to the adder. Therefore, here AC cos 2 pi fct, here AC kp Kp is the proportionality constant of the modulator, m of t sin 2 pi fct. The resultant will be the narrow band phase modulated waveform. So this shows the block diagram for narrow band phase modulator. So now we have the final expression will be AC Kp m of t sin 2 pi fct. This term, whole term will be negative. Therefore, AC cos 2 pi fct minus of AC Kp m of t into sin 2 pi fct. So this solves our time domain expression for narrow band phase modulated wave. We will move on to the next topic, frequency modulation. How to generate the frequency modulated wave. What is the time domain expression for frequency modulated wave? We know that Sfm of t is equal to AC cos 2 pi fct plus 2 pi kf integral over 0 to t m of t dt. So to simplify our expression, we are going to take this as phi. Therefore, our expression will be reduced to AC cos 2 pi fct plus phi. Now we can apply this cos of a plus b formula. Cos of a plus b is equal to, just now we have written cos a cos b minus sin a sin b. Therefore, by applying this form, we can rewrite this expression as AC cos 2 pi fct cos phi minus AC sin 2 pi fct sin phi. We know that for a narrow band, we are generating frequency modulated wave as well as phase modulated for narrow band version. For narrow band, beta will be less than 1. Therefore, our phi term will be less than 1. Cos phi is equal to minimum value is 1, sin phi is 5. Therefore, by substituting this, the above expression can be reduced to AC cos 2 pi fct. This whole term will become 1 minus AC sin 2 pi fct. This whole term will become 5. Therefore, 5. AC cos, by substituting the value for phi minus AC sin 2 pi fct. What is the value for phi? Phi is, we have 2 pi kf integral over 0 to t m of t dt. By bringing the constant terms in front, we can rewrite the expression as AC cos 2 pi fct minus 2 pi kf AC. Okay, we have AC term, this 2 pi kf integral over the sin 2 pi fct, also we can write it here, sin 2 pi fct integral over 0 to t m of t into dt. Now the job is to generate the block diagram. This is a time domain expression for narrow band modulated frequency modulation. Therefore, the block diagram is, we have to apply this m of t over an integrator. Therefore, the output will be integral over 0 to t m of t dt. The output is fed as one of the input for product modulator. The other input will be coming from the carrier signal. This is our carrier signal. This is 90-degree phase shifter. Therefore, here AC sin 2 pi fct, the output will be AC 2 pi kf proportionality constant sin 2 pi fct integral of 0 to t m of t dt. So, this is one output from the product modulator. This is fed to the adder, inversed phase and then fed to the adder, plus The output will be the narrow band frequency modulated wave. This part, have we seen this part somewhere else? Just now we have derived the block diagram for phase modulation. So this part can be effectively replaced by the phase modulator. Therefore, when a signal m of t is applied to the integrator and then fed to the phase modulator, this whole block is we have explained in the phase modulator. Therefore, phase modulator will give the output as S narrowband frequency modulated wave. So vice versa for it is when we apply m of t signal to a differentiator, and then the resultant, if we apply to the frequency modulator, the resultant will be S narrow, that is modulated wave for phase. This is frequency modulated wave and this is phase modulated wave. This is the relationship we have already seen in the phase modulation and frequency modulation title introduction. Therefore, if we are in need of phase modulation, if we already have a frequency modulated wave, we can easily generate our frequency modulated wave from a phase modulated wave, and then vice versa. Therefore, we can, it is more than sufficient to study the generation and detection for frequency modulation wave, because the phase modulation is in turn which is inbuilt in the frequency modulation. Now we will move on to the topic wideband frequency modulation. So far we have studied narrowband frequency modulation. Wideband frequency modulation. In short, it can be referred as WBFM. WBFM, wideband frequency modulation. We know the time domain expression for frequency modulation. So hereafter we are going to see only for the frequency modulation wave. Therefore, we know the time domain expression for frequency modulation. What is the time domain expression? In terms of beta AC cos 2 pi fct plus beta sin 2 pi fmt. This term don't have an imaginary part. Therefore, it can be rewritten as AC real part of e power j 2 pi fct plus beta sin 2 pi fmt. Since we know that cos theta is equal to cos theta plus j sin theta is equal to e power I theta. Since we don't have an imaginary part, we are simply replacing this theta value here. Therefore, the expression can be reduced as AC, the real part of e power j 2 pi fct into e power j beta sin 2 pi fmt. And this is a constant term, but this signal is a periodic signal with a period 1 by fm. Therefore, when we have a periodic signal, we will express it with the help of Fourier series. Therefore, with the help of Fourier series, it can be expressed as a periodic signal. If we have a non-periodic signal, we will go for Fourier transform explanation. If we have a periodic signal, we will go for Fourier series expansion. Therefore, periodic signal can be explained by using complex Fourier series. Why we are going for complex Fourier series? Since we have an j part here. Therefore, g of t is equal to summation over n is equal to minus infinity to plus infinity fn e power jn omega naught t. What is fn? Fn is the Fourier series constant. Therefore, what is fn? Fn is equal to 1 by t integral over minus t by t2 plus t by 2 g of t e power minus jn omega naught t dt. So, this is the Fourier series coefficient. Okay. Now, according to our expression, our g of t is e power j beta sin 2 pi fmt. Therefore, g of t is e power j beta plus j beta sin 2 pi fmt. And then what is the value for omega naught? Omega naught is equal to 2 pi fm. Then what is the value for t? This t is equal to 1 by fm. This is according to our expression. Therefore, we have to simply replace these values in this equation. If we take this as equation number 1 and this as equation number 2 and this as equation number 3, substitute all these values in equation number 3. Therefore, we know that Fn is equal to 1 by, since t is equal to 1 by Fm, Fn is equal to 1 by Fm integral over t by 2. Therefore, minus 1 by 2 Fm here plus 1 by 2 Fm. G of t will be replaced by e power j beta sin 2 pi Fm t. Then the second part is e power minus j n. The omega naught term is 2 pi Fm into n into t dt. By equating this 2 pi Fm, here pi term is missing. Therefore, by equating sine of, no, instead of sine, we'll only equate this term 2 pi Fm into t is equal to x. Therefore, dt is equal to Fm into dt is equal to 1 by 2 pi dx. Therefore, or to obtain this limits, that is to replace this lower limit and higher limit in terms of x, dt is equal to pi into dt is equal to 1 by 2 Fm into dx. Therefore, Fn is equal to Fm integral over this lower limit is, in this expression we have in terms of dt. Now we are going to replace in terms of dx. Therefore, the lower limit and upper limit value will get changed in minus pi to plus pi. 1 by 2 pi Fm is replaced with pi. Therefore, negative of s is minus pi. Therefore, e power minus j beta sin 2 pi Fmt is replaced as sin x. E power minus j 2 pi Fm is x there, right? Therefore, j nx into dx by 2 pi Fm. dt is equal to 2 pi Fm into dx. Therefore, when we take this constant term outside, Fm into 2 pi Fm integral over minus pi to plus pi e power minus j, plus j beta sin x minus nx, plus sign, right? Okay, into dx. This Fm and Fm will get cancelled. Therefore, 1 by 2 pi integral over minus pi to pi e power j of beta sin x minus nx into dx. This Fm. This is giving an important function in wave propagation, that we refer it as Jn of beta. E power j beta sin x minus nx is giving a famous relationship called the Bessel function. Bessel function is an important function for wave propagation, for studying and analyzing the characteristics of wave propagation. At this e power j into beta sin x minus nx is an Bessel function of first kind of order n and argument with argument beta. Therefore, we have generalized our Fn, this Fourier series coefficient, as Jn of beta. We have to substitute this term. We take this as equation number 4. We have to substitute this term in our equation number 2. Therefore, what will happen to our equation number 2? Can we write here? G of t is e power j beta sin 2 pi fmt that is substituting equation number 4 in 2. e power j beta sin 2 pi fm is equal to summation over n is equal to minus infinity plus infinity. Instead of fn, we are going to replace j n of beta e power j n omega naught t. We will take this as equation number 1. Now our job is to substitute our g of t in equation number 1. What is our equation number 1? Our equation number 1 is AC real part of e power j beta, sorry, j sin 2 pi fct, j beta into, sorry, we'll rewrite this expression again. S fm of t is equal to AC into real part of e power j 2 pi fct into e power j beta sin 2 pi fct, fmt. So this is our g of t. Just now we have calculated g of t is equal to summation over n is equal to minus infinity plus infinity j n of beta e power j n omega naught into t. Therefore, we are going to replace this term instead of e power j beta sin 2 pi ft. Therefore, our S fm of t, this equation number 1, will result as AC real part of e power j 2 pi fct summation over n is equal to minus infinity to plus infinity j n of beta e power j n omega naught is 2 pi fm. Therefore, e power j 2 pi fm t. This term can be represented as AC into real part of, when we take this term inside, summation over n is equal to minus infinity plus infinity j n of beta e power j 2 pi fc plus n into fm into t. Therefore, this whole term can be replaced as AC into real part of summation over this. Therefore, this can be replaced as AC cos summation over n is equal to minus infinity plus infinity cos of 2 pi fc plus n fm into t into j n of beta. This is a Bessel function term. Therefore, this is the time domain expression for wideband frequency modulated wave. Can we draw the graphical expression for this? When our beta value is equal to, that is 0 to 1, when we have n value is equal to 0. This is j of 0 of beta, j n of beta. This is Bessel functions, plots for Bessel function of first kind. Next value is j 1 of beta, when I have n value is equal to 1. This is for j 1 of beta. When I have j 2 of beta, again. When I have j, this is for j 2 of beta, and this is for j 3 of beta. It goes on like this. This is the plots of Bessel function. So it shows this, it is the time domain expression. So when we convert this time domain expression into frequency domain expression, our waveform will be, it have infinite number of sideband frequencies, that is AC by 2 summation over n is equal to minus infinity to plus infinity j n of beta this cos 2 pi fc plus nfm of t can be represented as dou of f minus fc plus nfm plus dou of f plus fc plus nfm. So this is a frequency domain expression. Therefore, when we draw the spectrum, so this is the origin 0, this WB FM of T. Center frequency of the carrier minus FC, AC by 2 into J naught of beta. Here again AC by 2 into J naught of beta. The sideband frequencies so these are the sideband frequencies. It goes on like this, infinite in terms of f. Therefore, this value is fc plus fm, the second is fc plus 2fm, the third value is fc plus 3fm. It means that sideband frequencies are spaced symmetrically on either side of the carrier at frequency separation of fm, 2fm and 3fm. This fc minus fm, here fc minus 2fm, here fc minus 3fm. So it goes on like this. This is the amplitude spectrum of wideband frequency modulation. We know that in amplitude modulation will have center frequency, that is main component, along with the two sidebands, either upper sideband and lower sideband here also. But we have infinite number of sidebands in wideband frequency modulation, which are equally and symmetrically separated by a distance of fm, 2fm and 3fm. Now the magnitude of Jn of beta is determined by the amplitude of the nth band, because each function is having a different amplitude which is determined by the nth sideband. Therefore, what are all the inferences we have seen so far? For the wideband frequency modulation, infinite set of frequencies. Therefore, it means that how to calculate the bandwidth by taking the lowest frequency, highest frequency minus of lowest frequency. But theoretically, we have infinite bandwidth here. But theoretically, the first inference we have from the wideband, the first inference we have observed from the wideband frequency modulation is theoretically we have infinite bandwidth. We are going to see in the next few minutes how we are going to limit for our practical purposes. And when beta is small, we have values for J0 of beta and J1 of beta. That is, we have only the carrier plus two sidebands. When beta is small, then it looks like narrow band frequency modulated wave. When beta is greater than 1, till which value it will be significant? When till this n value is approximately equal to beta, the amplitude values will be significant. After that, 98% of carrier power distribution is occur only within this limit, that is when n is approximately equal to beta. When n is greater than beta, it have negligible values. When is very greater than beta, it gives only negligible values. And the fourth inference is amplitude remains constant. So we know that, therefore average power is Wfm of t, which is equal to AC square divided by 2. And efficiency is always 100%. Next, we will move on to what is the transmission bandwidth for the frequency modulated wave. Transmission bandwidth. Just now we have seen theoretically it has having infinite frequency, but it is not practically implementable. Therefore, we have to restrict our bandwidth, in which based on which parameter is we are going to study. Therefore, we know that if beta is small, we have no issues. Therefore, when beta is small, transmission bandwidth is equal to approximately equal to twice the FM. Since we know that lower sideband frequency and upper sideband frequency, this is the USB minus of FC minus FM. This is the upper sideband frequency and this is the lower sideband frequency. Therefore, to calculate the bandwidth, FC plus FM minus FC plus FM, therefore, these two will get cancelled, 2 into FM. This we already see. Therefore, when beta is small, the transmission bandwidth is approximately equal to twice the modulating frequency. In case if we have a beta large, that is, we have a beta value very greater than 1. What will be the case? Jn of beta is approximately equal to 0 when I have n is greater than beta. That is, it have a significant value only when n is equal to beta. After that, that is 98% of power, total power will be lying only in this region. When n is greater than beta, it is negligible, therefore insignificant. Therefore, we can restrict our bandwidth till n is equal to beta. Therefore, significant component range is FC minus NFM plus NFM. This is the significant component. Therefore, FC minus beta FM, FC plus beta into FM. Therefore, transmission bandwidth, this is transmission bandwidth, but can be represented as FC minus plus of beta FM minus FC minus beta FM. It can be generalized by using Carson's rule, 2 into beta plus 1 into FM. But actually this formula will result in 2 beta into FM, but Carson, he generalized Carson's rule. Carson's rule is beta 2 is equal to 2 beta plus 1 into FM for all values of beta. This is the transmission bandwidth according to the Carson's rule. According to the Carson's rule, when we rewrite this equation in terms of frequency deviation, beta t is equal to 2 into del f 1 plus 1 by beta. And in terms of deviation ratio, beta t is equal to 2w d plus 1. Next, we are going to see generation of frequency waves. In this, we are going to see the indirect method and direct method.